let's have a little fun talking about shock waves here. Shock waves. So a shock wave is caused when you have a disturbance propagating through a medium faster than the speed of sound in that medium, which means, if you will, that the waves being created is that basically, well, so if something's moving faster than the speed of sound, any sound that is generating can't get away from it, can't get out in front of it, as it were. You can have a similar phenomenon on the surface of water, where if something is traveling faster than the speed of water waves, ripples traveling across the surface, you get a similar phenomenon where the ripples that it's creating aren't moving as fast as the thing is, and they can't get away, they can't move out in front of it. So let's talk about the second of those situations. Here we have a stationary boat that's bobbing up and down in the water. And so as a result, ripples are spreading away from it, forming circles on the surface because they are all centered on that same point. Just wanted, I couldn't remember if I started a recording or not. If the boat is moving along slower than the speed of the ripples, then you'll get that each new ripple is centered in a different location. So you get a pattern like this. This is the classic idea behind the Doppler shift, the Doppler effect, where the wavelength is shorter in front and longer behind because the waves pile up in front as you've got motion, each wavefront being created in a new location, stretched out behind. If the boat is moving faster than the ripples, then you get the formation of what's called a bow wave, where you get these two lines along the surface of the water where the wavefronts line up with one another, because you can't have any of them in front of the boat because it's moving faster than the ripples do. And similar diagram for sound coming out of our jet. If it's subsonic, then in front of the jet, you've got shorter wavelength, higher frequency. Behind the jet, longer wavelength, lower frequency, just plain old Doppler effect. Get the jet moving faster and faster, and when it punches through the sound barrier, so to speak, well, the sound waves have been built up more and more in front of it, and then literally when it crosses the sound barrier, when it starts going faster than the speed of sound, it'll punch through that, and then afterwards, you get what's called a shock wave. And this would be in 3 dimensions. It would be the surface of a cone surrounding it, where the sound wave fronts overlap one another. And shock waves are associated with compression. Material is compressed when a shock wave that's moving faster than the speed of sound passes through a medium. And so here is, I think I can click on this and get this animation showing what's going on. It's fun. Let's see. I want to, this type of file can harm your computer. Yes, I want to go ahead and keep it anyway. No, I didn't want to download it. Let's run it. Welcome to Windows. Okay, are you going to play it for me? Because you can play it for me if you like. Sure, I'll use recommended settings. It's probably going to keep working there. It's just going to laugh at me, right?
And virus.
Mm-hmm. Great. It was awesome. Yeah. And this, of course, will make all the difference, right? Because what is it about stupidity? It's like doing, oh wait, to play it, oh, you must install the Adobe. Yeah, but let's see if Firefox likes it better. That's where I want to remote, they can turn that off in the background there. Let's get through Gmail. Sign in. No, I don't know. Gmail probably easy. No, drive.google.com. Excuse me.
Firefox looks like we will not allow you to do this. Change it to German.
That'd be mean. Well, this is exciting, isn't it?
Ooh.
Ah.
Yeah, thank you.
Sort of. No, just stretching.
Yes, please do. Oh, wait, of course. Oh, my phone buzzed, so I heard something. Okay, very good. Yes, indeed. Yes, I do want to do that. Okay. Okay. And so now, wow, this is just so exciting. Oh, okay, good, because this up here because I opened it today. Well, that is exciting, because I'm excited. I know you're not, so that's kind of neat.
Nagule.
Please, please, please work.
Don't want forehead?
Activate Adobe Flash. Allow and remember.
Remember.
Remember. Come on. Woohoo! Okay. All righty then. So, we have here a microphone that I can drag out in front. And this lets me, here's my source of sound waves. It's sitting there, and you can't hear anything, so that's not really that crucial, but it's still part of the entertainment, so I guess I'll turn the speakers on. Let's start it moving. Doppler shift. I've actually got it moving at 98.4% the speed of sound, or light if you wanted to think of it as light. If I slow it down some, you have like that situation going like before. But the idea is, let me reset this. We'll get it over here and maybe a little off to the side. So, let's go through the sound barrier. Crossed, and there you see this idea of there's the bow wave, as it were, or the shock wave. Yes,
This is what the dinosaurs said.
it is. And because it's just too friggin' cute, I always have to include that not only boats, but also, okay, stop it Firefox, we'll just go back to, okay, full screen it. We'll just go back to our buddy, Google. It's a ducky! And the ducky is paddling through the water faster than the ripples that the ducky is making, and so the ducky is, because you have to say ducky. The ducky has a bow wave behind itself. And it's easy to see that if you've ever been on a boat. It's not hard to get a boat to move faster than the water ripple speed on the surface of the water. And that's why you get that triangular thing spreading out behind the boat. It's the overlap of the ripples that can't get out in front of the boat, basically. Meanwhile, this is a photograph of a shock wave passing through the interstellar medium in the Orion Nebula from HST. So there's some shock waves labeled there, which are compressing the surrounding material. So now let's get to the point where we can understand this figure, which is describing commodus collapse. So let's talk about one of your homework problems is to do the quick and dirty rough calculation of the more detailed calculation that we're about to do now for the free fall time scale. the timescale associated with a portion of a cloud collapsing to form a star. I decided I needed another injection of caffeine for the third hour.
It's important to say.
Yes, yeah, well, to stay dehydrated since it's kind of a net diuretic, right? Caffeine. But it's actually, turns out it's not important to stay dehydrated. Although there have been cases of like athletes overdoing it in terms of hydration, and that can be fatal because you mess up your electrolyte balance.
There was the one story so many years ago when the league came out with this one lady. She was so convinced that she needed to win or leave her family. She entered in a water drinking contest
Oh, whoops.
and drank like 2 gallons of water. And one of the stipulations of the contest was you couldn't go to the bathroom.
Double whoops.
So she ended up being sent to the hospital because there was an oversaturation of water in her blood.
Mm,
And
yeah.
I don't know if she died or not, but the story was that she died. But I saw that video about the situation.
Yeah. Not good.
Or your cells would explode.
Well, then Tycho Brahe, supposedly he died when he was at a banquet, and he didn't want to go to the bathroom, and his bladder burst, basically. That's how he supposedly died.
This investigation.
So basically, when you gotta go, you gotta go.
Nature calls.
When nature calls, listen to her. Yes. All right, formation of protostars.
Woo! Third out.
We're going to learn about the gene's mass and the gene's length.
Throw your genes out.
My gene's length is 34 inches.
Mine got 31.
31?
In this
Yep.
weird spot between 30 and 30.
Yeah. Yeah, I need a tailor, basically.
Yeah.
Clothes don't fit me, really.
I got these pants and that.
Show me the video.
What?
Show me the video.
Do indeed.
Especially on airplanes that are flying for a long
Yes.
time and want to sleep.
Well, good thing you're not running any of those anytime soon.
No. Actually, last time I flew to Europe, my feeling was this was so short because of having flown to Asia. You know, it's like, so there's only 7 hours. That's great. You know. Sir James Jeans, who lived from 1877 to 1946, and I have to say it like this because he's Sir James Jeans. In 1902, was the first to investigate the conditions necessary for an interstellar cloud to collapse. God, I'm so bad. Anyway.
Just write ASTR right over.
Yeah. Yes, kind of that. Oh,
It's okay to fast forward.
yes, please fast forward. If you're British,
Live your song.
then, yeah.
You got all the money right.
Disclaimer, we're about to offend a lot of people.
Well, it's not offensive, but it's for the British.
Right.
Or the Italian.
Well, actually, I think I'm just more making a fool of myself than offending anybody. They're just like, to offend, you kind of have to have a basic level of competence, you know. And I kind of,
I'm not competent enough to offend anyone.
That's right, yes. Was the first to investigation. Well, see there, to investigate.
Oh, man, I never. But by the criteria that you need to be competent enough to offend people, Donald Trump should never be able to offend anyone.
Oh, I guess I have to throw that hypothesis out the window.
Hey-o.
The conditions necessary for an interstellar cloud to collapse. Fundamentally, the inward force of gravity must exceed the outward pressure gradient force. gravity force must exceed the outward pressure gradient force. Well, the way we're going to look at this is via your favorite and mine, the virial theorem.
Too soon.
Too soon. Too soon. Well, in the spirit of there was lightning and thunder yesterday, virial theorem already this semester.
Dun, dun, dun.
Yes. So, you will recall that the virial theorem says that in equilibrium, twice the kinetic energy plus the potential energy is equal to 0, whereby this kinetic energy, what we're talking about is not the bulk kinetic energy, we're talking about the microscopic kinetic energy, the total energy associated with molecular motions, also known as, starts with a T. You're taking another class, potentially, that's about what kind of physics? Thermal energy. Kinetic energy is the thermal kinetic energy.
Starts with a T. That's usually-
Yeah, and there's a D.
No,
Starts with
no,
a D.
That was like
Oh, sorry. Thermal energy.
Thermal energy.
Yeah. Right.
dermal energy. It's up the
Yes.
skin.
Thermal
So-
energy. That's the T side.
If 2k plus u is equal to 0, that's the condition for virial equilibrium. Pressure gradient balances gravity. Cloud is in virial equilibrium. You can also just say equilibrium, but since we're using the virial theorem, we can say virial equilibrium. Well, if the cloud's going to collapse, it shouldn't be in equilibrium. So there's two possibilities, 2k plus u is greater than 0, 2k plus u is less than 0. If 2k plus u is greater than 0, that means you got too much thermal energy. Is that going to mean that the cloud's going to want to expand or want to collapse? It's going to want to expand. Excess thermal energy means higher pressures, the cloud's going to want to expand. So in this case, the pressure gradient exceeds gravity. So the cloud expands. This is not what we want for star formation. So what we must want is 2k plus u is less than 0. Pressure gradient less than gravity. Cloud contracts. Ding. That's what we want. We want this. But that means that 2k plus u equals 0 is the limiting case. So in other words, if we want to look at where we're on the border, we want to look for that limiting case. So let's consider a spherical cloud of uniform density, just to keep things simple. I almost assigned a homework problem, which was calculate the gravitational potential under a spherical cloud. And then I remembered that that would be like the 17th time that you had done that sort of thing, so I didn't. For a spherical cloud of uniform density,
It's just the luminosity error.
what?
It's just the luminosity error. That one, the thermal, whatever. It's that problem we kept getting every single time.
Yeah, right, yeah, well, there's that too, yeah. But this one, I think you've seen this one too, like if it's got uniform density, find its potential energy. We did it in E&M for charge, and I think we did this last semester for mass, you know, from a ball of mass and so forth. So I know you've done it before, but yeah, all right, yeah, the one you were really talking about, right, was there's a grain and it's so many AU from the sun, and how warm will it be? That sort of thing, yes. For a spherical, but it's a very important problem, so it doesn't hurt to do it 14 times. For a spherical cloud of uniform density, I mean, I find by the 15th time I've done something, I'm getting pretty good at it. For a spherical cloud of uniform density, the gravitational PE is U equals, so it has to be something, it's negative because it's bound. It has to be something that has the right units. So remember, potential energy for two masses separated by distance r is g m1 m2 over r. So if we're doing it for a cloud, what makes sense is, okay, you need mass squared, right? Mass m1 m2 has units of mass squared. What else could there be but the square of the mass of the cloud? You need something to serve as a distance. What else could there be but the radius of the cloud? And then there's got to be some factor out in front that takes care of the details of this is a uniform cloud, or the density varies in this way, that sort of thing. For a uniform cloud, the factor works out to be 3/5 out front. So that's the gravitational potential energy. What's the thermal kinetic energy? Well, that will be 3/2 times total number of particles in the cloud times Boltzmann constant times temperature. So that's dredging that up from your memory too. That's a consequence of the equipartition theorem. You'll see it again in StatMech if you haven't already. Did you just see it? Okay, very good. Oh, excellent. That's awesome. Okay. So here n is total number of particles.
So you guys,
What's that?
feels like in sync even without the trees.
I know. That's right. Yes.
It's just one big long derivation of that.
Yeah.
Seriously.
I'm just, well, it takes a moment, yes, but I'm just pulling it right out here. We're just using the result. Yes. So that'll be 3/2 times the mass of the cloud divided by the average mass per particle. Or in other words, the mean molecular weight times the mass of a hydrogen. So that's another thing I'm digging up from your memory from last semester. So here is the mean molecular, mu is the mean molecular weight. And mH is the mass of a hydrogen. So total mass divided by the average mass per particle is going to be the total number of particles. Mu mH by definition is the average mass per particle. Mu is the average mass per particle, mean molecular weight in terms of the mass of a hydrogen atom. So now we can look at what's the condition to be right on the border. 2K is equal to, well actually let's look at the condition for 2K plus U is less than 0. There's not enough thermal kinetic energy to produce enough pressure to support the cloud. So 2K is less than the absolute value of U, because remember, K is positive, U is negative. So we want 2K to be too small, smaller than the absolute value of U, which the absolute value of U is positive. 2K being less than U becomes, absolute value of U becomes 3 times the mass of the cloud times K times T divided by mu mH is less than 3/5 times G times the mass of the cloud squared, or the radius of the cloud. We just literally plugged in 2K and minus U there. That's the value of U. So, if that condition holds, the cloud will want to collapse. But we want to put this in more useful terms. So we're going to use that the mass of the cloud is its density times its volume. Or in other words, it'll be 4/3 pi times the radius of the cloud cubed, that's its volume, multiplied by rho cloud, that's its density, plug that in, and solve for the radius of the cloud. So in other words, plug in this mass on both sides and solve for the radius of the cloud. What we get is the radius of the cloud. Oh, sorry, that's stupid. Okay. Ignore the last sentence. What I really mean is, okay, so solve for the radius of the cloud in this expression, not being all fancy, we're going to do that later. Solve for the radius of the cloud, that says the radius of the cloud is, I was making it way too complicated, 3 times the mass of the cloud divided by 4 pi times the density of the cloud to the 1/3 power. So now if we put that back in to our previous expression, and we're going to flip it around. So I'm going to reverse the inequality here. I'm going to flip the left side and the right side of this inequality. 3/5 G times the mass of the cloud squared, and then 1 over the radius of the cloud, using that expression right there, is, just flip that over because I'm dividing, 4 pi times the density of the cloud over 3 times its mass to the 1/3 power will be greater than, because I've reversed the order, so when you have an inequality, if you change the two sides, of course the inequality also turns around as well, is greater than 3 mass of cloud kT over mu h. Now we can cancel out one factor of mass of cloud over there. And now we've got the mass of the cloud divided by the mass of the cloud to the 1/3 power, which is the mass of the cloud to the 2/3 power. And if we move the other constants to the other side, this is mass of the cloud to the 2/3 power is greater than 5 kT over G mu mH 3 over 4 pi rho cloud everything else to the other side besides the mass of the cloud. These threes cancel as well, clearly. So now let's raise both sides to the 3/2 power to just have an expression for the mass of the cloud. For the cloud to want to collapse, for gravity to be stronger than pressure inside of it, the mass of the cloud needs to be greater than about. We say about because we assume that it was uniformly dense. You know, we made that approximation, that it was spherical. We made some approximations. We say greater than around here. 5 kT over g mu mh to the 3/2 power, because we're raising both sides to the 3/2 down to the 2/3. And then when we raise blah to the 1/3 to the 3/2, that becomes to the 1/2. So 3 over 4 pi rho c to the 1/2 power, because 3/2 times 1/3 is 1/2. And by definition, the quantity on the right-hand side there is m sub j, the Jeans mass. So the mass of the cloud needs to exceed the Jeans mass for the cloud to want to collapse. So essentially, if you know the parameters of some interstellar cloud, you can calculate its Jeans mass and compare it to its actual mass, and that tells you, is that cloud going to want to form a star, or is it just going to be in equilibrium and not going to form a star, or maybe even expanding? It can also be useful to talk about the Jeans length. How big does the cloud have to be for a given density in order for it to want to start collapsing? So, any questions at this point? Alrighty. We can also find an expression for the Jeans length. We just need a ruler. No.
You need a tailor.
You need a tailor. That's right, yes. You need a ruler and a tailor, and then you can find your Jeans length. And that's it.
We have officially reached
Well,
that
yeah.
order.
Yeah. Boy, that was a long setup for a bad joke, wasn't it?
I thought we were doing physics today.
Yeah. This is where, yeah, this is where you switch to that like meme of the dog that has that smile, you know, whatever, right?
Like Dogecoin.
I'm almost tempted to cut
Mark,
that out of the video and post it and see if anybody gets it. Which is the minimum radius needed for a cloud of a given density to collapse. So we're going to start again with the expression we had before. Starting again with 3/5 G mass of cloud squared over R cloud is greater than 3M cloud KT over mu MH. Might as well flip the inequality now. We have G times the mass of the cloud over the radius of the cloud is greater than 5 kT over mu MH. In other words, just divide 2 by the mass of the cloud and then multiply by 5/3 to get it off of the left-hand side. So a very simple step there. And then let's once again use the fact that the mass of the cloud is its density times its volume, 4/3 pi r cubed rho. So G over the radius of the cloud times the mass of the cloud, which we'll write as 4/3 pi r cloud cubed times rho cloud. The rho cloud is missing in my notes apparently, is greater than 5 kT over mu MH. So now, just solve for the radius of the cloud. Now it's just r cloud cubed over r cloud just gives r squared. So we're going to take the square root. So the radius of the cloud should be more than about, after you multiply by 3/4 and all that, 15 kT over 4 pi g mu mh rho cloud to the 1/2 power. That quantity is the G's length. And following an example in the book, let's throw in some numbers for some specific cases. Okay, so we talked about these various aspects of the interstellar medium. Okay, so any questions? All right, so we'll finish up today by doing this example here. Diffuse H1 cloud. To diffuse H1 clouds collapse to form stars. Let's find out, shall we? For a diffuse H1 cloud, let's use 50 Kelvin as its temperature. Let's use 500 particles per cubic centimeter as its density. Let's assume falsely that it really is pure neutral hydrogen atoms. What's the mean molecular weight in that case? 1, yeah, 1, very good. Yep, just being sure you had that idea. The mean molecular weight would be 1. So the cloud's density would just be the mass of a hydrogen atom times its number density. Right, number of particles per cubic centimeter times the mass of each particle. That gives you 8.4 times 10 to the minus 22nd grams per cubic centimeter. Which we can convert to kilograms per cubic meter if you want. You just have to multiply it by 1,000 to do that. 1 kilogram per cubic meter is 1,000 grams per, 1,000 kilograms per cubic meter is a gram per cubic centimeter. Density of water is 1,000 kilograms per cubic meter, 1 metric ton per cubic meter. Anyway, with mu equals 1, what we get when we put in the numbers for the gene's mass is that it is about 1,500 times the mass of the sun. That's way more than the mass of an H1 cloud. Which greatly exceeds the 1 to 100 solar masses of such clouds. Conclusion, ain't no stars forming there. That ain't no star forming region. On the other hand, we claimed before that dense cores are sites of star formation. Let's plug in their numbers. Dense cores, Bach globules. We'll use 150 Kelvin for the temperature. That's a typical value. We'll use 10 to the 8th per cubic centimeter as the density. We'll use same assumption about the composition. No, we can't do that because it's a giant molecular cloud, so it should be molecular hydrogen, but I didn't put that in here. Whatever, so we're just going to write it down, but it's probably off by factor 2. Anyway, the density would be like, if we made it mass of hydrogen times the number density, that would give 2 times 10 to the minus 16 per gram per cubic centimeter. So I have to double check that and see if that's off by a factor of 2, but in any case, it's not going to really change the conclusion. Leads to a gene's mass on the order of 17 solar masses. Well within the observed range for such clouds of 10 to 1,000 solar masses. Conclusion. Stars can form here. All right, so next time we'll do the homologous collapse.